videos. The third one is going to be an overview for the samples of the previous reports. Now, the other part now is going to be the virtual lab number 1. Again, we will start with downloading this file. Oh, one of the questions was asking last time about, I will tell you what he done exactly. It's not actually a bad thing, but something like a lack of experience. If I would like to get one of these videos working, I'm not going to go to the MATLAB and start to run it from there. The MATLAB doesn't have a video player. So for example, we're going to go to Virtual Lab or the Pendulum. You will see that one of the files we're going to have is going to be a video, MP4. You don't click it here. It's not going to work. It doesn't have a video player. So if you would like to watch the video, which is within the files, this video, just double click on it, and then it will.
Hello, and welcome to this video. I'd like to present.
So I will play this video for you. It's going to be 8 minutes. And then we're going to apply everything he's done in our work. So once again, the thank you. Okay, so you will see that in this example, I'm going to close this one. Don't say. Yep. So in this example, what's the scenario? Okay, so we're going to have the pendulum and it's going to hit the block. The block will be sliding. Unless we're going to hit it at a certain height with a certain friction, and this may cause it to tip off. We want to know what will be the mass for the red ball and the mass for the green ball and the height for the impact position and the coefficient of friction, the minimum values to make this block tip instead of slide. This will be the next stage. The first stage is only going to check the effects of the mass and how far it's going to push it to. So what do we call this scenario? Among the section that we learned, did we have anything actually similar to that one? I can tell you it's not, because usually what we had was we consider every one of these two systems individually in the subject. We had a part which been hit by a force to make it move. That's what we call the impulse force, right? You remember? And also we have the pendulum that's going to hit a surface and then stop. That's mean it's hitting the wall. And that's what we have in the case of the, which was the case, I think that yeah, for the case for the, it was also the impulse momentum. When the bar was falling, then it's hooked and start to move and hit the wall. So it's going to be two different models has been joined together. Again, this will be something like 2 degrees of freedom for each part. And by joining them, this is have 2 degrees of freedom. This one is going to have 3 degrees of freedom, and such we're going to have 4 degrees of freedom. If this one is going to be tipped off, then we're going to have another degrees to make it up to 6 degrees of freedom. Again, I unlock the file, and then I can simply drag and drop, not this one, this folder. I can drag and drop this folder to my math space folder. Okay, now you can see that we're going to have 1, 2, 3, 4 scenarios, and we're going to go through them very briefly, but first let's watch the video.
Just a really quick overview of this virtual laboratory that allows you to study the dynamics of this pendulum and block friction case study example. From the animations that you're looking at on the screen right now, hopefully it's pretty self-explanatory. We have a pendulum, which consists of a yellow rod with a point mass pendulum bob. The pendulum can swing and it can impact another mass, the green block mass. The green block mass is resting on a table and it can slide across the table. So the main focus of this virtual lab is studying the sort of friction effects between the green block mass and the table that it's sitting on. Okay, so there are 3 tasks in this virtual lab. We'll only talk about the first 2 in this video. In task 1, it's really quick. We simply introduce a MATLAB script that allows you to load into MATLAB's workspace numeric values for the model parameters that we've used to characterize the model by. How do you load into the MATLAB workspace a numeric value for the pendulum mass? How do you load into the workspace numeric values for the green block mass? So task 1 is about loading into the MATLAB workspace numeric values for our model parameters. The second task, we introduce you to the Simulink model that is a model of this pendulum block system. And we'll also look at the cause and effect workflow that you and your students can go through. All right, so let's look at tasks 1 and 2. So each task has its own dedicated MATLAB live script. So here's the task 1 live script. And as you sort of scroll down it, you can sort of see the instructions for what you need to do with this script. And for this task 1 script, it's nothing more complex than simply hitting the green run triangle, which simply runs the entire contents of the live script. So when you run this script, you'll see over on the right-hand side of the screen contents of the MATLAB workspace. We've now loaded into MATLAB's workspace variables that allow us to assign numeric values to our model. For instance, if I was to interrogate this variable called block, you can kind of see that it's got all of the numeric values for things like the mass of the green block and so forth. And similarly, if I interrogate the pendulum variable, you'll see, again, the pendulum's rod length, the pendulum's mass, the pendulum bob diameter. Okay, so this is all task 1 has done for us. We've just simply loaded into the workspace, MATLAB variables. These MATLAB variables are used by the Simulink model that we're about to look at next. So just let me sort of scroll down to the bottom of task 1, and I'll click on this link that says task 2. So here's the dedicated MATLAB script for task 2. And as I just sort of scroll down, all this task is about is getting you to open the Simulink model of the system, and then we'll simulate the model. And then we'll look at 2 particular experiments where we sort of vary, the mass of the pendulum, the mass of the sliding block, and so forth. So as I scroll down it, the very first main step is to open the Simulink model, which is simply clicking on this button. There it is. And this is the Simulink model for this pendulum sliding block case study. Yeah? So this graphical block diagram is the graphical language used by Simulink and Simscape for assembling these physical models of mechanical systems. So in order to run or simulate this model, we simply go to the big green run circle. Would be this one, and we click on it. And when you do, this nice sort of CAD-like animation figure appears automatically. And as you can sort of see, it does a replay of the machine as it's sort of propagating forwards in time. And you'll notice some hopefully fairly explanatory, self-explanatory controls down here that you can sort of interact with a slider bar, and do a playback to sort of re-watch the results of the simulation. Okay, all right. So that was running the model out of the box. Let's go back to the task 2 live script. So the workflow of the task 2 script is there are 2 experiments. So let's just go through the first one. It's an almost identical workflow for the second experiment. But in the first experiment, what we're going to sort of do is we're going to go back to that MATLAB script that defines the MATLAB model parameters, and we're just going to sort of configure them. So we'll configure the pendulum bob mass to being 5 kilograms, and the green block that's sitting on the table to being 3 kilograms. All right, so let's go and do that. So here's our task 1 script file. And you'll see that the sort of parameters that we sort of want you to sort of interact with are kind of signposted by the slider bars. So the first one was the pendulum bob mass, M. So let's set that value to 5. And the block mass of 3 kilograms is already set. All right. So when you actually interact with these slider bars, what it does is it actually runs the MATLAB code within the script. So that in the MATLAB workspace now, we have the updated versions of these variables that, for instance, has a value of 5 for the pendulum bob mass. All right. So we've got our experiment parameters already in our MATLAB workspace. Let's go to the simulate model. In fact, I kind of think the viewer, going to the viewer is a better option. If you go to the viewer, again, just look for that big green simulate icon, and that will simulate the model with these brand new model parameters. Yeah, so let's do that. Might kind of look very similar to the previous one. If I was to really quickly go back to the task 2 script and have a look at experiment 2. Experiment 2, we're going to set the pendulum bob mass to 1 kilogram. So let's go to our parameter script, find that pendulum bob mass slider bar, adjust it. Our MATLAB workspace now has the updated versions of these model parameters. If I go back to my viewing window and click that green simulate icon again, you can see the cause and effect of this particular set of parameters. So there you have it. That's a really quick introduction of how to sort of interact with the MATLAB scripts and the simulate model of this pendulum sliding block virtual laboratory.
So we're going to apply the same thing that he done, well, which is, as I told you, that for me, I'm not doing any coding. I just show you the steps in an easy way. Okay. Most of the equations, as I told you last week, you can get it from the same code. If they are not there, like this example, you can make some like your own research to find these equations. So once again, we're going to go there. I already have the file available for you. Again, to go to the BH file and start to search for it after you upload it there. We're looking for the virtual lab of the pendulum and the impacting of the block. Again, I divide things into multiple steps. I get to start with the start here as usual. Right-click and open. And the last one is going to be about the tipping, and the other one is going to be first change the parameters, make the model, and run the simulation results. Again, for the part that doesn't have any numbering, you don't have to run the sections. We're only going to go through it to read what's happening here. Okay, so that's what's happening. We just did it, and it's going to be pushed further. The lower velocity have multiple reasons. What are the reasons that in the one to the left, the block has been pushed slower than the one to the right? What could be the possible reasons for that? Yeah, and higher coefficient of friction for the left one for me. Okay, the mass of the green block is higher. So all these stuff are possible reasons. Again, if I get to take the link for the pendulum to a lower value for the theta, it's not going to have enough force to push the block. We're going to increase it. This will have a higher momentum to cause the work. So these are the apparatus we have. These are what we have as definition. The mass of the block is M capital. The LP is the pendulum rod length. D is the pendulum bob diameter. The L1X is going to be the horizontal length of the block. The L1Y is going to be the vertical length of the block. The HY is going to be the length of the pivot points above the table. And the K, mu S, and the mu K, these are the static and the kinetic coefficient of friction. And this is a scala that allows us to specify the impact point on the block. So this value should be between 0 and 1. So later we're going to start with task number 1, but before we get to go there, let me see if I can update this part. No block has been actually generated. Anyway, click here. Well, nothing has been updated because we don't have any parameters has been entered here. Now we will go to task number 1. Loading the drive, pendulum block, the motor parameter on X. Maybe I did something wrong last day. Let me try to do it from here. Okay. Now, if you're going to have a similar problem, you don't have to think about a solution for it. What you are going to do. Don't have to worry about that. Just go to the model. I'm going to go up to here. I will go to the file that I downloaded here, look for the file that actually have a problem, click on it, and delete it. And get it back once again. You're always going to have a fresh copy on your downloads. Just bring this fresh copy and put it on, because maybe I did something last day, and this caused that the error to be presented. So I get to drag and drop this one here. What says here? Maybe I put in within another section. So drag and drop. The empty folders. Why is empty? Wait a second. Go to downloads. Yeah, right. Cancel. Okay. So again, that's the pendulum. Go to downloads. I download the file here. And again, to extract all to the download. Yes. Okay. Yeah, now it should be available. Let's close this one. And that's the virtual lab. Now it's working. Yep. Okay. So whenever you have a problem, don't think about a solution. Just simply remove it and get the fresh copy of it. All done. Close. Okay, now we have a fresh copy of that. So we'll go back to here. I'll look for this copy and again to open it. So this is virtual lab import the block thing. And now again to start to do the work again. Again to open this one first. File not found. Okay, maybe it's going to need some time to fresh. I don't know how it's end up to have one inside the other, but anyway, hopefully this one is going to work now. Yeah, it's working now. Okay, so as we said earlier, that we're going to jump to task number 2, task number 1. Now the file is working. Now, most of the thing here that you don't have actually an equation has been given to you this time. And this requires you actually to find the individual conditions for that. For example, we can make a basic research about the case of so the analysis, dynamic analysis, or the forces analysis. Okay. Pendulum impact block. Maybe you're not going to get the exact similar one, but definitely you can find one. Response of the impact in volume. If you look for the images, you will find more details about that. Okay, so you can get to any one of those and try to get some of the equations if you want. Actually, let's read and let's see what the other people done and find out what they have done earlier. So impact breakaway wind resistant base connection. No, this is not actually what we need to do. And actually, this is quite a complicated issue. Let's look nice work. Okay. Maybe you will do that later in your capstone. Actually, I will save this file. I liked it. Yep. And now that's what's that experimental of the impacting Pendulum system. Yep, that's the one, but it's going to hit a wall. So it's going to be something similar to the example that we've done earlier. Okay, so we expect to get a similar result in the model we're going to work on. Anyway, so the parameters first need to be updated, and that's what we're going to have here. We'll create the MATLAB variables that will be used in our Simulink model of this system. And these models variables will be simply going to be defined in the base of the MATLAB workspace. So we are in the live editor. We are going to change these parameters. I can change the pendulum mass to be from 1 to, I think, 5 kilograms, and the length of the link from 0 to 1 meter. So first, once again, we start with the clear. I'm going to do the clear. Okay, and then I'm going to change the parameters here. So the pendulum mass, I'll put it something like 2 kilograms now. The length of the link, I will leave it as 0.5 meters. The road density is given in kilogram per cubic meters. The pendulum diameter is 0.05 meters. The pendulum width is 0.0015. And the position L, X, Y, Z has been given. Now the block parameters, the mass, I will make it quite heavy. I will make it the heaviest, actually. I will make it to 5. The K value, the block LIX, which is where the position of the heading will be. All this stuff going to be calculated, depend on what you are going to put as parameters here. Okay, so this can be changed here. Okay, and the initial condition has been defined. The block parameters has been defined. The measurement sampling in how many seconds is going to be has been defined. The coefficient of friction between the block and the table has been defined. And then we're going to go to the last point. This is surface contact parameters also been defined. And now again to run this one to update the parameters. Next step, we're going to go to the task number 2 and try to run the things. But for that, let me execute this section. Okay, then again to run the other model. Now this will give us the Simulink model. Again, that's description of what you're going to need to do. We have 2 experiments and you can make them 3, and this will guarantee some extra marks for you. We have a video like the video that we just saw, and we're going to open the Simulink model by clicking here and change the time step to 5. You can make it anytime you want. And then we're going to explore the cause and the effects by changing the parameters. And that's what I'm done actually. I took the pendulum mass to 1 kilograms. That's for my experiment. And made the length to be the same, and the block mass, this is a 3, I made it 5. So I'm going to have a heavy mass for the block and low mass for the pendulum and see what will be the results. We're going to run it. We're going to find the results. We're going to take these results, write down some discussion, and then we're going to do the other test by changing the mass for both and rerun it once again and see what will happen. So once again, the steps is going to be start by click here to open the model. Now we can see that the Simulink model is updated. And if I would like to explore what we have here, that's the pendulum block model. It consists of 2 parts, which were going to be the model itself and the data logger. Definitely all the results is going to be in the data logger. So I will go to the model. I don't have actually any output from here. The data logger does. So all the results will be coming here, which is going to be the block position, the block velocity, the pendulum position, and the pendulum velocity. So when I'm going to double click on that after the simulation, I will get the results. Now, I think that last day we were not able to actually see the things correctly. It's once again going from the, oh no, actually it's worked now. I hope it will work. Okay, so again, I hadn't changed the time for one reason, because it's already set to 5 seconds. You can change that and you can check what the difference between those. So click on that. Okay, so just push it. So it's push it to a decent level and start to have a continuity movement for the pendulum. This is not going to be important. The main important is going to be about. At this position, it didn't tip it off. Second is the distance for the displacement was quite low. If I would like to update the parameters, I need to go to the actual Simulink, the actual model where we change the parameters here and change the parameters, execute the steps until we're going to get the final answer. Okay, so once again, that's the model, that's the Simulink model. And let's try to get some of the graphs. Okay, so again, simply do that. And also we have another option here, which is file. You can print to a figure. Okay, and I'm not going to do it here because this will be saved somewhere on the cloud. But on your computer, definitely you can have it directly, or you can use the snapshotting software that I shared with you, and you can take a snapshot of the whole thing and make it as an image. Again, I can click on that, and this will scale everything to be in the middle. If I would like to find any of these parameters, I can use the lens. Okay, so let's see what will be the time when the clock position will stop sliding. So it seems to be somewhere here. Okay, so it's something like 0.955 seconds, within the range of 0.945 seconds to 0.955 seconds. Okay, that's when it's going to be stop sliding and remain in the position of 0.4 meters. Sorry, yeah, that's the position. That's the velocity, which is going to be dropped down because the friction force will resist the movement. Okay, so again, you just need to do at least 2 of the experiments. You can choose a third one if you want, it's optional. And you can get the results and find out the difference between both scenarios. Again, I'm not going to run the second one now. I'm going to go for the task number 4, which is going to be about the tipping block over the table. Now, the goal of this one is, we said that the K value should be anything between 0 and 1. One of these values is going to cause the things to be tip over. So for this task, we will use a different simulation model to one used in the task number 1, 2, and 3. And specifically, we are going to add an additional rotational degree of freedom and allowing the block to both translate and rotate. Rotate in case if it's going to be tip over. So it's all going to depend on this value. There's a critical position. After that, when you're going to kick it, it's going to start to rotate. Well, how many of you actually was angry at a certain time and he kicked a box on the ground? Try it next time. That you don't have to be angry. So you will see that actually, depending on the position, you'll find out if the block is going to be just sliding or it's going to be hit. So the parameter is going to be the same. I don't need this parameter in that case, so I'm going to put it clear. And I'm going to actually have a new fresh command window as well. Okay, now these are the parameters we're going to add. You can see that the other parameter we're going to have is going to be the viscous damping coefficient of the pivot point B and the K value that's already been defined earlier. All these parameters will be now to be changed. So we will create the MATLAB variables that will be used in our Simulink models for this system. And these model variables will be defined by the base MATLAB workspace. So we're going to go once again and change the parameters. Start with the clear. I did that. The G is going to be the same, unless if, okay, now when the G value will be changed. Are you going to have the same G value if you are going to be at the top of the Mountain Everest or near the Dead Sea? It will change. This can be dropped to 9.6, as can be up to 10.5, depending on the elevation we're going to have over the sea level. Because this depends on how far you are from the Earth center. Okay, so now we're going to use it as 9.81 because in this position, we are almost 5 meters above the sea level. Okay, so again, the parameter will be changed. It's going to be the L1, sorry, the block height. I will change this one to a quite high level. I will make it as 0.5 meters, that height. For the block mass, I'm going to drop that to 3. For the block K value, I will make it to 0.75. Let's say it will be something about trial and error. Okay, for the other parameter, I will leave them as it is. And now we come to the pendulum. I will make it quite heavy. Okay, the diameter of the pendulum will be 0.08. I will leave those things as they are. The block parameters, part 2 of 2, is going to be calculated. The pendulum value will be calculated. Okay, so this will be for the block conditions, initial position for the X and the Y, initial velocity in the X, and initial velocity of the Y. The surface parameter, which is going to be about the coefficient of friction and the other stuff, you can change that. You can actually check what will be the coefficient of friction between different materials, and this can be added as well. This is a critical velocity as well. And now we have everything ready. Just simply click on that. So as long as it's going to be hash line, that means it needs to be updated. So update that. Now we're going to have the Simulink model for the 6 degrees of freedom is going to be generated by clicking this block. But let's see what he wants you to do. So experiment number 1, you're going to set the parameters for the Ly to be 0.25, for the block mass to be 5, for the block K value to be 0.5. And now go to the Simulink model and run the model by running, and then going to check what will be the block to be tipped over, and you have to say what it had in. Then you're going to change the parameters for the block to be 0.25, block mass to be 0.5, the K value to be 0.1. Remember that I put on the max, how much I put here? The K, 0.75. So I expect that my box will be tipped. I don't know, we'll check that. Experiment number 3 is going to be about perform a few repeats. Experiment number 2, change the value for the K. You make it less than 0.5, you make it above 0.8, and see which one is going to work. Okay, so just run this one first. Then I'm going to go to the Simulink model, and then I'm going to run 2 scenarios for you. The one I just made, and one of the experiment we have. So actually, that's the model we have. We're going to have the model, and we're going to have the parameter view time series signal. That's the model inside the box. Okay, and this will be the measurement of the 6 degree of freedom. You can see here that we're going to have the rotational possibility around the Y, the X, and the Z, and the position X, Y, Z. Contact point system is being defined already by using the multiple ready blocks, and this will be the time series. Now we can have the position X, Y, Z for the block, the rolling possibility of the rotation around the X, Y, Z, and we have the velocity. The other thing for the pendulum, we're going to have the position in the X and the Y, and the velocity magnitude as well. Now we're going to run the simulation. Yeah, actually, I think that the one that, wait a second. Oh, yeah. Actually, I tipped it because the K value was high. Okay, so it was heavy mass, light mass, high level. So when I run it, boom. Okay. So now we're going to see what will be the parameters. Later, we're going to change the K value to be a quiet low. So we're going to double click on that. It's not responding. Okay. Once again, we can click on that to centralize everything. Okay, so just remember that these blocks are unused, so you cannot find any text above them. You can decide actually what will be the number of the used one by number of the inputs for the plots. So definitely it's not going to accept an odd number most of the cases. I mean, you cannot make 5. You should have these things to be appeared, but it's going to have no data with them. Okay, so once again, this will be about the position in X, Y, Z. This will be about the rotational possibility. This one is rotated around the 3 axes, so actually we hit it too hard. The velocities in the X has been calculated. The position for the pendulum in the X, Y, and the velocity magnitude has all been done. Okay, now next step is, I'm going to close that. We had, sorry. Okay, so that's only about the rotation and the position for the block, the same one that we had on the other one. So now I would like to change the parameters, so I can simply just go to here, and I'm going to drop the value for the L to be I'll make it as 0.3. Okay, and the block mass will be 3, but the K value will be 0.5. And let's see what will happen in this scenario. Remember to update that. And after that, we're going to run this simulation again. So I'm going to run the simulation here. Okay, so obviously what's happening here that the block didn't tip. Okay, now what's happened is I lowered the position that I hit the box. Now it's in the middle. It didn't tip. Now the last thing we're going to try is we're going to hit at the bottom, less than 0.5. So again, we're going to go to the parameters and change that. I'm only going to change the K value, and I'm going to make it something like, let's make it S.2, and update these parameters. Okay, and we'll go to this one directly. Okay, now we are going to, sometimes we can run it from here, sometimes we can't. Anyway, doing. So again, it's tipped it off, but now the rotation is going to be in opposite. Okay, so actually people who play in soccer, they understand how these things is working, right? The position away from the center that causes the ball to rotate or just going straight forward. Okay, so yeah, that's the only thing you need to do for this experiment. Then you're going to take the results and write down something about it. Okay, by the way, there's another way you can do for your presentation. In the presentation, you don't have to put too much text. I know that they say that the presentation length should be limited to 3 minutes. It doesn't have to be 3 minutes for me. You can go up to 4 minutes and 4.5, and there will be no problem. What you can do in the presentation is that you're going to discuss one of the 4 scenarios we have, but both people in the group should talk about that. You can make some videos like the software I told you about. You can make a video for these things and put them on. If you think that the file is going to be quite large, you know how to make the GIF files, right? Actually, once again, people like you can make the use of the internet as much as you can. Just go GIF creator online, and I think that the EasyGIF is the first one of the best. You just bring your actually you can make it for the video from video. Yeah, so you can bring your video to here, and then you're going to decide what will be the time frame you would like to change it to GIF image. So most of my lecture slides for the one you saw in manufacturing, I was using this website to do the things. Okay, yeah. So I think that's it for the for this Simulink issue, and we're going to start closing that and going to stop the video. And the last thing we're going to do today, and actually in this semester in the class, is going to be have some examples for the previous projects. Let me close that, and then we're going to start a new video, and we're going to actually check the reports. Okay, now we're done with this one. I don't need any more. Leave the page. Okay, so now this step is going to be about stop the recording.